In activity 4, we're looking at polarity, both bond polarity and molecular polarity. So let's look at bond polarity first. And remember that bond polarity occurs when bonding electrons are shared unequally in covalent bonds. And the way we determine if a bond is polar or not is we look at the difference in electronegativity between the two atoms in a bond. Electronegativity values are found on page 4 and on page 23 of your lab manual. And we're going to use the criteria that's stated in your lab manual to identify a bond as ionic, nonpolar covalent, or polar covalent. So if the difference in electronegativity is between 0 and 0.3, that bond is going to be considered to be nonpolar covalent. If the difference in electronegativity is greater than 0.3, up to 1.7, then that bond is going to be considered to be polar covalent. And if the difference in electronegativity is greater than 1.7, the bond is ionic. Now again, when we're looking at this difference of electronegativity, it is just the absolute value of the difference. So for activity 4, it tells us in instruction number 1, complete data table 2 using the periodic table of electronegativities and the bonding scale to determine the type of bond that each set of atoms would exhibit. For polar covalent bonds only, draw a vector between atoms showing bond polarity in the last column. So here is data table 2 in your lab manual. You can print this out. You can also use the data table 2 that I created for you. And you can find that on the last page of the data tables. So right here in this first column, you look at the two atoms, write out their electronegativity difference, then determine whether the bond is nonpolar covalent, covalent, or ionic. Only if the bond is polar would you fill in this last column, and what you're doing is drawing a bond from the less electronegative atom to the more electronegative atom. That's what they mean by those vectors. So I know that hydrogen and oxygen is a polar bond. Oxygen has the higher electronegativity, and so the arrow is going to be pointed towards the atom that has the higher electronegativity. Then the rest of activity 4 is filling out data table 1 and tells us to determine the electronegativity difference and bond polarity for each bond for the compounds in data table 1. Record your calculations and bond polarity determination under activity 4 in data table 1. So you can use the data table that I've created for you. I have an extra column here for the chemical formula. Clearly state how you calculate the electronegativity difference. For example, I've written out that sulfur has an electronegativity of 2.5, oxygen has an electronegativity of 3.5, and the difference of 1. If there is a polar bond, then we draw an arrow from the less electronegative atom to the more electronegative. Since the electronegativity difference is 1, and that's between 0.4 and 1.7, this is a polar bond, and oxygen has the higher electronegativity. 3. Add appropriate bond polarity vectors besides each bond in the perspective drawings under activity 3 in data table 1. So let's go back to activity 3, data table 1. Here we are. And there are line drawings, this perspective drawing, and here's the perspective drawing for sulfur dioxide. Again, it's in a plane, so there's no wedges or hatches. And in black is the line drawing. Again, E is the lone pair. So because this is a polar bond, I'm going to draw an arrow from the less electronegative central atom to the outer oxygen atom, which is more electronegative. And I'm going to draw one for every polar bond that there is. So sulfur oxygen arrow, pointing towards the more electronegative atom. So if your chemical that you've chosen has a polar bond, go back to data table 1, activity 3, and draw arrows from the less electronegative atom to the more electronegative atom, only if it's a polar bond. And then 4 and 5, we're looking at the molecular polarity. So determine whether your molecule exhibits a dipole moment, and if it does, write yes. If it doesn't, write no. And then determine whether each molecule is polar, and write polar or nonpolar. So remember, a molecule will have a dipole moment if the central atom has a lone pair or if the outer atoms are different. So you have the Lewis dot structure for all of your molecules in data table 1 for activity 1. I look at sulfur dioxide, I see the central atom has a lone pair, so therefore it has a dipole moment. So I write yes under dipole moment. And then here it is polar, so I'm going to write polar. So every time a molecule has a dipole moment, yes, it is polar. Every time it doesn't have a dipole moment, so no, meaning the central atom has no lone pairs and all the outer atoms are the same, so no dipole moment means it's nonpolar. So N and N. No dipole, nonpolar. Yes dipole, polar molecule.